The topic we are going to discuss today is basically it's all about the transition elements, D block elements. And when we come across the periodic table, we find a very important block at the center, which is called the transition elements. They possess unique chemical and physical properties, making them vital for daily use. Copper is used in wiring, coins, and plumbing, while iron is essential for bridges, vehicle parts, and construction. Chromium enhances plumbing fixtures. Gold and silver are valuable for jewelry and electronics. Platinum aids in catalytic converters. Titanium is used in bicycles, aircrafts, and artificial joints. And nickel, vanadium, molybdenum, and tantalum. They serve various industrial and medical purposes. Transition metals also form alloys such as brass, which is a mixture of copper and zinc, and bronze, which is a mixture of copper and tin. So in this chapter, transition metals are explored. So here in this paragraph, we need to learn about the uses of different metals, transition metals, and alloys like brass, which is copper and zinc, Cu and Zn, and bronze is copper and tin. So transition elements are those which have incomplete D subshell in their most stable ionic states. They have been given the name transition, which means change, because they show gradual change from much reactive group 2 elements to much less reactive group 13 elements. So the first period of transition elements starts from scandium to zinc, and however zinc does not qualify the definition of transition elements because it forms only one colorless ion Zn2+ with a complete 3D subshell. Although zinc can form complexes like transition metals, but this is not sufficient for it to be included in the transition elements block. Scandium was initially controversial as its common +3 oxidation state has an empty subshell. However, it was later included in the transition metals by IUPAC system when compounds with +1 and +2 oxidation states such as SCCl3 were synthesized. Okay, zinc is a D block element but not a transition element. Because transition element, when we see the definition of transition elements, are basically those which have incomplete D subshell, and zinc, if it's in Zn2+ state, it have complete 3D subshell. So it doesn't come in the definition in the category of transition elements. Okay, now we have to look at the electronic configurations of D block. The electronic configuration of transition metals follows Aufbau principle. However, there are some exceptions to this rule. For example, chromium and copper break Aufbau principle. The reason is that atoms or ions with a half-filled 3D subshell or filled 3D subshell sublevel are relatively stable, avoiding the interelectronic repulsions in 4s orbital that occurs with the 4s2 configuration. Moreover, in both cases, the 3D electron cloud is symmetrical, which shields the nucleus relatively in more effective way. So chromium and copper, basically they break the Aufbau principle, and the reason is that atoms or ions with a half-filled filled 3D subshell are relatively stable, avoiding the interelectronic repulsions. So this is the reason. Key information: when forming cations, electrons are always removed from the higher energy sublevel 4s in the first row of D block element. Scandium +1 and +2. 4s1 and 3d1, and scandium +2 is 3d1. 3d2 and 4s2 is 3d2. Argon 3d2 for titanium +2, and so on. We can write the electronic configurations. Now we'll talk about the relative energies of 4s and 3d subshell. The energy difference between 3d and 4s orbitals changes across the period. In calcium, the 4s orbital has lower energy than the 3d orbital because the 4s electron experience full attraction. This makes the 4s electron more penetrating than the 3d. A long 3d period after calcium, the 4s electrons are shielded by the 3d electrons, slightly decreasing their energy, causing small rise in the first and second ionization energies. On the contrary, the 3d electrons faces higher effective nuclear charge due to less shielding, strongly attracted by the nucleus. This results in the potential increase of 3d electrons, reflected in higher rise of third ionization energy. Properties of transition elements. So transition elements have physical properties, and transition elements are much more like each other than the elements across period 3. For instance, they are all metals rather than showing a change from metal to metalloids and non-metal. On the other hand, when we move along period 3, there come metals and metalloids, non-metals and noble gases. Similarly, there is not that decrease in atomic radii as in period 3 element. Due to such similarity, transition metals show the following physical and chemical properties. Atomic radii of vanadium and zinc is same because its shielding offered by addition of 3d electron countered the effect of increasing nuclear charge. Physical properties. Physical property, they have high melting points, they have high density, they are good conductor of electricity, they are good thermal conductors, they have shiny metallic luster, they are malleable and ductile, they are hard, and they show magnetic properties like paramagnetism and ferromagnetism. Physical properties are density, atomic radii, melting and boiling points. So we will see it one by one. Density. So density of metal is mass per unit volume. So it's an important physical property. Moving through first period of transition metals from scandium to copper, the density of transition metal generally increases. This is because of the two factors. Atomic mass of the metals are increasing and the atomic radius decreases. So there is a strong pull of the nucleus. Since density is directly related to mass and inversely related to volume, the increase in mass and decrease in volume across the period generally lead to an increase in the density. However, there are some exceptions. The density of manganese and copper is different from what is generally expected. The atomic radius of zinc is larger than that of copper because its full 3D subshell leads to less tight packing of zinc atoms in its metallic lattice, resulting in reduced density. Atomic radii. Transition metals show specific trends of atomic radii across the period. Understanding these trends require consideration of both shielding effect and electronic configuration. In the first two transition elements, the atomic radii decrease across the period because the nuclear charge increase, pulling electron closer to the nucleus. However, unlike main group elements, this decrease is less steep because the electrons being added in the 3D subshell does not shield one another sufficiently from the nuclear charge. In the beginning, atomic radii decrease because of the increasing nuclear charge. The decrease in atomic nuclei is not that pronounced while going through the middle of the period because of the two factors, increasing nuclear charge and shielding effect, counterbalance each other. In this way, the atomic radii remain almost constant. So at the center of the period, the atomic radii remains constant. Moving towards the end, atomic radii increase from nickel to copper and zinc. The reason is that 3D subshell becomes full, which causes shielding effect, pushing 4s subshell away from the nucleus. Similarly, when moving from copper to zinc, we see an expected increase in atomic radius. The atomic radius of zinc is larger than that of copper because the additional electron in the 4s subshell is zinc, increases the shielding effect. Melting points and boiling points. The melting and boiling points of transition metals are generally higher than the S and P blocks, and they have strong metallic bonding. And we plot metallic and boiling point against atomic number, and then we get two minima at manganese, which reflect that the full 4s and half 3D subshells are much stable. Magnetic properties. Transition metals and their compounds show magnetic properties which provides us information about chemical bonding. An electron spinning around its own axis generates magnetic field, just like the electric current flowing through a wire. It means a single unpaired electron acts like a small magnet. Based on unpaired and paired electrons, transition metals and compounds show different magnetic properties. Paramagnetic. Paramagnetism substances are weakly attracted in the magnetic field, for example, aluminium and sodium. The reason is that they have unpaired electrons. The unpaired electrons on atoms or ions are not influenced by the electrons on surrounding atoms, so they are directed randomly. When a paramagnetic solid is placed in the magnetic field, the magnetic moments are aligned parallel to one another and net weak attraction is observed. However, when the magnet is removed, the solid loses its paramagnetic properties. Ferromagnetic substances are strongly attracted by the magnetic field, for example, iron, cobalt, and nickel. They also have unpaired electrons in the valence shell, and the unpaired electrons influenced by the electrons of surrounding atoms and ions and align in the same direction. When a ferromagnetic substance is placed under magnet, a very strong attraction is observed, nearly million times more than a paramagnetic substance. Ferromagnetic substances maintain their magnetic moment even after removal of magnetic fields. Diamagnetic substances are those which are weakly repelled by magnet because they have paired electrons in outermost shell. For example, copper and iron. The paired electrons in orbit cancel out the individual magnetic moments, making net magnetic moment 0. Alloy formation. Alloys are the mixture of metals. Transition metals can form alloys. They can substitute one another. Steel is an alloy of iron, chromium, nickel, and manganese. And other examples of alloys are brass and bronze. Chemical properties. Chemical properties are basically, first is the variable oxidation state, and the common oxidation state for the first row of D block is +2, which is obtained by the loss of 2 4s electrons to form M2 plus ion. And manganese has the electronic configuration 3d54s2 that have the maximum oxidation state of +7. The stability of +2 oxidation state compared to +3 oxidation increases with increasing atomic number. On the other hand, the stability of the higher oxidation state decreases with atomic number from left to right across the series. Catalytic activity. So, the transition metals also act as a catalyst in most of the reactions. First row of transition metals, they have the unique property to change their oxidation to exist in different oxidation states like iron and copper. So they temporarily change their oxidation state by gaining or losing the electrons. During chemical reaction, help reactants convert to products. At the end of the reaction, they regain their original oxidation state and become ready to play their role as a catalyst again. These metals possesses incomplete 3d orbitals. These vacant orbitals can accept electron pairs from ligands, forming temporary dative bonds between the transition metals and ligands. These dative bonds are responsible for holding reactant particles on the surface of transition metal. Resultantly, the bonds within reactant particles weaken and ultimately break. The product formation takes place on the surface of transition metal. In this way, transition metals speed up the reaction. After completion of reaction, transition metal releases the product and becomes ready to bind again. So in the Haber process, we all know that in the Haber process, we have the basically iron is used as a catalyst in the Haber process, which involves the formation of ammonia. Similarly, in the contact process, vanadium pentoxide is used as a catalyst. And on the other hand, we have hydrogenous catalyst, which where reactants and catalysts are in the same physical state. For example, oxidation of iodide by peroxodisulfate ion is 2I negative plus S2O8 2 negative gives us 2SO4 2 negative plus I2. This reaction is slow because the negatively charged ions of reactants repel each other. It can be catalyzed by the addition of D block metals. So 2Fe plus S2O8 gives us 2Fe3 plus 2SO4 2 negative. Fe plus 2I negative gives us 2Fe2 plus I2. So this is basically the reaction in which the oxidation state is changing. Now we have the ligand. Ligand is an atom or group of atoms which is electron rich and can donate lone pairs of electrons, making dative covalent bond with them. Ligands may be molecules or ions made up of non-metal atoms. They are also called Lewis spaces or nucleophiles. Based on the number of lone pair, they can contribute to coordinate covalent bond. Ligands have the following classes. Monodentate ligands. The ligands which can form one dative covalent bond with transition metal is the monodentate. They may have more than one lone pair of electrons. For example, aqua, halo, and hydroxoamine and cyano. The ligand that can donate more than one lone pair of electrons are polydentate ligands. For example, 1,2-diaminoethane and ethane dioate are bidentate ligands like oxalato and ethylene diamine. Similarly, ethane diamine tetraethanoic acid ETTA is a hexadentate ligand and it can donate 6 lone pairs of electrons to the central metal atom. So this is all about today. Thanks for listening.